time for a new gas law. Let's start with the combined gas law, which states that pressure times volume divided by the absolute temperature is a constant. And let's take Avogadro's law, which states that volume divided by the amount of gas is a constant. Well, it's a different constant. And these two laws are very useful because they allow me to predict changes. So for the combined gas law, if you, for example, tell me how the pressure and the temperature is changing, I can tell you how the volume will change. But you have to keep a fixed amount of gas. For Avogadro's law, if you tell me how the amount of gas is changing, I'll tell you how the volume is changing. You got to keep pressure and temperature constant. Well, what if I want to change pressure, volume, temperature, and the amount of gas all together? I can't use one or the other formula. I have to combine them. So let's go back up to Avogadro's law. I just did a mathematical rearrangement. And in some ways, this, I think, more clearly shows that as you change the amount of gas, the volume changes. Now, if I take that same idea and plug that into the combined gas law, this now shows that pressure, volume, and temperature is dependent upon how much gas. So this makes it a formula of state for a gas, and just talking about pressure, volume, temperature, and the amount of gas, not changing conditions. So this allows me to do things like say, here's the pressure, here's the volume, here's the temperature. Tell me how much gas there is. But I do have a problem. That C1's a problem. That's just a constant. I just labeled it C1 because I have a C1 and a C2. That's all two different constants. We've labeled it capital R for the ideal gas constant. It's possible that this was named after Henri Victor Regnault, who was a French chemist in the 1800s. They may have honored him by giving the value, the letter R, after his name. That's not the way that it's usually shown. It's usually shown this way on the bottom. PV equals nRT. The ideal gas law. R is a constant. And if I tell you pressure, volume, and the amount of gas, then you can tell me the temperature. Or we can kind of mix all that up. So there are 4 variables in there. I give you 3, you tell me the 4th. Okay, as long as we have a value of R. This is a very common value of R. 0.082057 liters atmospheres per mole Kelvin. There are a few other values of R depending upon what unit you like. Well, here's a Wikipedia page on the ideal gas constant. And the ideal gas constant is experimentally determined. And then all the other ones are derived from that based on unit changes. And, well, here are a few. Here's a joules per Kelvin mole. Ooh, here's the atmospheres one, liters atmospheres per mole Kelvin. And we got a few. Let's see. Here are some more. Here are some more. Oh my goodness. Here are some more. Oh my god, it's not stopping. Here are some more. Oh, whew, I ran out. Okay, so there's quite a few values of R. How many do you have to worry about? These are the 3 values of R I give my students. I don't make my students memorize the values of R. Now, why 3? Let's first look at what's different between each of these in terms of units. And it's pressure. I chose these three based on pressure units. The top one because atmosphere still shows up in chemistry and other areas, still a useful unit. Torr because of its relationship between millimeters of mercury, and millimeters of mercury still shows up in some areas. And then the bottom one, bar, because the bar is based on the SI unit of pressure, the Pascal. Now, all three of these have 5 significant figures, which is sufficient for any calculation, I know at least that I give in my classes. When you use a value of R, the way I prefer to do it is to pick the value of R that corresponds to whatever pressure unit you're worried about. What I see in a number of chemistry textbooks is that they'll give the first one, sometimes I see the second one also, but usually I see the first one. And then they have students convert pressure units, if they're different than atmospheres, into atmospheres. So you'd have to convert torr into atmospheres and use the top one, bar into atmospheres and use the top one. Okay, but why not just work with 3 values of R? And I stopped there because I didn't want to overwhelm people with even more. You saw how many units there were. There are even more if you want to start changing around and throw in milliliters and things like that. So this is sufficient. When you write out R to do a calculation, it can be challenging because look at the units. You have liters, pressure units over moles, Kelvin, and then times a value. So let me suggest something. When I work the problems out, I'm going to distribute the units across the numerator and denominator. So for that top value, that's what I really have. It's really 0.082057 liters atmospheres all over mole Kelvin. This will help you from making common unit mistakes when you have to divide by R. I can do the same thing for the other 2 values of R. Watch your units and how you distribute them.